So it's a pleasure to have John Realpe-Gomez from the Universidad de Cartagena with us today. So please. Yeah.
Okay, thank you very much, Marcus, for the introduction. Thank you, all the organizers, for the invitation. Do you hear me well in the back? It's okay? So I'm very happy to be here. I was a diploma student at the ICTP, so I'm always happy when I'm at ICTP. And I will talk today of a work that I started developing when I was working in the Universidad de Cartagena in Colombia for a while. I joined a project that was competing in Europe for, I think, 10-year funding. It was a big project, Future ICT. And they were opening a Latin American node. And through them, I started a collaboration with people in Italy. I will mention later. So I started this project. And then I moved to NASA soon afterwards. And so I essentially largely developed this project on my free time. So it's not my main, the main focus of my career in the last years, which has been working in quantum artificial intelligence, first at NASA, and then recently at Xanadu Quantum Technologies. So I will be very happy. It's the first time I present this work, so I'll be very happy to have your feedback. Okay, so I understand this is a conference, a school, sorry, for students. I have been talking to some of them, undergrads, graduates, postdocs. So I would like to first give like a big picture of the take-home message for you, and before entering into more details. So this is like a kind of beautiful patterns other people have been showing here. Ricardo was showing something related to this. So the question is why this beautiful self-organization? You surely know about this. At the very least, we expect if these individuals communicate locally, how they can organize globally. So at the very least, we require some long-range correlations and some sensitivity, some responsiveness, such that the system, when one individual in one corner moves, say, that information can propagate quickly through the system. Now, what is interesting is that there are analogies in physics, for instance, in magnetic materials, where you can have what is called a second-order phase transition, where by varying the temperature, at low temperature, the system is well-organized, very ordered. Then if the temperature is very high, the system is very disorganized. And in between, there is something very interesting going on. Correlations are very long range. And if you just do a little perturbation in one corner of the system, it can travel far away. The system is very responsive. So there are a lot of interest here by biologists. I think Curtis Callan has done some work, Viale has done some role related to this from Princeton, and there are many people working on this. So there is the question, these are biological systems. Does this provide an evolutionary advantage? So there was a beautiful paper, in my opinion, recently that suggests there might be an evolutionary advantage of being near this kind of critical point where the correlation length can go to infinity. So this is my final slide for students, I would say. This is another system where I have ants. This is, it was published by a team in Israel, Nature Communication recently. You have ants, and they sort of have three types of behavior. One of them is some of them go to explore around, trying to find information about the direction they should move. And some others, they got together all around a load that they need to push towards the nest, let's say. And the question is how they manage to do that. So these guys propose a model that they fit very well with experiments also. And the basic idea, they managed to simplify the model to something called Ising model, which is very simple, mean field model, which is the most simple model, I think, of critical behavior. And the idea is they can balance this. The main message of this work is the ant groups can balance ants, individual ants, balance between two strategies. One is individuality, which is just they randomly pull up the load and they do nothing else, or conformity, they lift the load to reduce the friction, or they pull in the direction of the majority. And there is conformity, which is just pulling in the direction of the majority. And there is a parameter that sort of interpolates between these two things. And that parameter happened to be, again, near a critical point. So the main message of this work here is that ants, apparently, according to this experimental evidence, apparently balance between individual behavior and social behavior close to a critical point in order to optimize the transport of the load. Okay? So, and this is very analogous to what we found in our work, which is this thing here, that is the take-home message. Essentially, we can have a network of humans interacting, playing a prisoner dilemma game, for instance, where they have to cooperate or defect, okay? This is an abstract game, the experiment, they just select to cooperate or defect in a computer. But in practice, in real life, it could be something as important as reducing carbon emission or not. So that's a very important kind of problem. Now, so individuals here, this is a model that we try to build, taking into account experimental results that have been obtained recently. And essentially what we do is we have this, every individual balance as ants, like ants, every individual balance between their individual interest to maximize the profits or the payoff, and also what others are doing, the social, what we could call the norm around. The norm that they perceive in their environment. Now, by doing so, according to the evidence, I mean, this is not conclusive evidence, of course, it needs to be further studied, but the evidence that we provide is that by doing so, these individuals, by balancing between selfishness and prosociality, they pose close to a critical point again. Another example of critical point that you might be more familiar with is, for instance, this is the diagram of the water, H2O. This is the diagram of the water, and you know that there is a boundary between liquid and vapor. But that boundary disappears at some point. So if you move here, there is no boundary there is no distinction between liquid and vapor. Where this boundary finishes is very special. It's, again, one critical point, long-range correlation. Water looks more or less like milk. So, yeah, that's more or less the take-home message of this work. Now, so the outline of the talk would be...
What's the analog of temperature and pressure?
What is what, sorry?
So what is the order parameter? What is temperature and pressure?
In here?
Yeah.
No, there are no temperature and pressure. There is one parameter that is balancing how much weight you give to the individual behavior versus the social behavior. There is one parameter. But I'm not saying that this looks exactly like the pressure-temperature diagram. I'm just trying to illustrate to students that they might be more familiar with this kind of diagram from undergrad, that there is a critical point here. And the system poses close to a critical point, but the parameters are totally different. I will show in the next slide. Okay? Sorry? Yes. Well, I don't have the critical exponent, but I have the critical point. I didn't work the critical exponents, but yeah. So, by the way, you are interested in criticality. There is a school here in July that will have a course on that, on criticality. So the outline of the talk will be essentially, we'll speak about cooperation and why it is considered sometimes like a puzzle. Then I will consider evolution. This is a conference about evolution, so I will try to connect evolution and learning of cooperation in a very simple way. Then I will speak criticality as an evolutionary advantage. That's the work of Hidalgo that I mentioned before. Then I will mention just a few experimental results, recent experimental results that are not performed by me. I'm not an experimentalist. So, and then I will introduce the model, which is empirically based and analytically tractable. So we can find the phase diagram of the model, we can find critical points, and so on. And we can infer the parameters from the experiment, and we can locate where the human groups are in this phase diagram. And then we'll discuss this near criticality, but I think the most relevant here, because there are young students here, is the perspectives that I think could be here. So for the future, for you. So the puzzle of cooperation. So as you already saw this, Luca introduced this game in his first lecture. Essentially, I think most of you may know this. So you have two prisoners that have been caught by doing some crime, right? But there is not enough evidence. So they are put in jail separately, and they are asked to confess or to remain silent. They have these two possibilities. And what happens is that if they both confess, then the authorities has enough evidence and they go to jail for 5 years, both of them. If instead both remain silent, then they have only 1 year each because there is not enough evidence. But now there is a temptation that if one confesses and the other remains silent, the one who confessed gets free for collaboration, and the other goes 20 years. Gets 20 years. So this is kind of the situation. This can be codified in payoff matrix. You see, this is numbers here, 5, 0, 21, 5, 0, 21. That's the idea. Okay. So in the case of the prisoner, in this prisoner dilemma again, cooperate is to remain silent, which doesn't seem to be very helpful for society. But as I said, cooperate can also be reduce CO2 emissions. So, okay, now there is, as I say, there is the following situation that these guys say, should I confess or should I remain silent? Now, suppose that this guy confess. The one who remains silent get 20 years. If he remains, this one confess. Now, if this guy remains silent, he gets 20 years. Otherwise, he gets 5 only. So he has a preference to confess. Now, if this guy remains silent, again, this guy is 1 year if he remains silent, but gets 0 years if he confesses. So once again, he has a tendency, a preference to move to confess. And the game is symmetric, so the same happened to this guy. So they both end up here, which is called the Nash equilibrium of the game. They both end up in this situation. Now, what is called the dilemma is that this is a better outcome for both. So this is the dilemma. So the question in biology has been, one of the questions in biology has been why then cooperation is sustained, why cooperation persists. So, and then you have evolution, for instance. This is a work by Nowak and Nature. Essentially, they consider a repeated game where players have fixed strategies. As you know, this is very much what Luca discussed in the first lecture. So you have essentially a population of players. Here I represent them in a network, everybody interacting with everybody else. So this is a well-mixed population. But if now the guys, they play a fixed strategy, and depending on the outcomes of the game, they look around and they imitate the best. And this is the next round. They change a strategy by imitating the best neighbor. But since the guy that defects is the one that will win most, at the end, all these guys will imitate this guy, and cooperation will collapse. So cooperation collapses in well-mixed populations in this kind of framework, in this particular framework here. But then what Nowak realizes was that if you put a structure, if population has a structure, it's not well mixed, for instance, it's in a lattice, they manage to survive. Cooperators manage to survive by forming clusters, sort of groups that defend each other, and the guys on the boundary sacrifice themselves for the group, in a sense. Now, you saw this again, once again, Luca was speaking about this thing. So this is a two-population model. Consider a two-population model, for instance, where you have cooperators, individuals that cooperate, and individuals that defect. And here there is another population. It can be also represented by a histogram, for instance, or by probability distributions, which are here. okay? And the idea is now, in evolutionary game theory, the payoffs are interpreted as fitness, so, or as reproduction rates. And so you have now these guys, players from here, interact with play prisoner dilemma games with players randomly chosen from here. And depending on the fitness, the one that gets the highest payoff has the highest probability to reproduce. And so this is an evolutionary model. And then we can get, in this way, as you, most of you may know, a replicator equation, which is this is the time derivative of the probability, and this is the kind of terms that Luca was showing in the lectures. Okay, this is the payoff matrix, and so on. Now let me show you how this is related to learning. And this is the idea that you just speak about a population of ideas. You imagine that this is actually an individual, and all these strategies that are, this population is a population of potential strategies they can play. You can think there is a population of neurons, I don't know, maybe. There are some people that say that we encode probabilities as populations of neurons, but probably not. But in any way that we encode this in our brains, this is like a population of ideas here. And the other guy also have a population of ideas. So they follow very close, a very similar dynamics of the evolutionary dynamics. Indeed, we get, again, a replicator equation here, except that we get a new term, kind of entropic term, associated to memory loss. So if the guys are, I will come back to this later.
Sorry, the ideas are interacting within each individual or among?
It's exactly as a two population replicator equation in biology. So you just, one idea from here, it plays, let me say like that, like one idea from here plays a game with one chosen random idea from here, and the one that has the better payoff has a higher probability to reproduce within this individual. It's like two population evolutionary dynamics.
Are you assuming that the payoff function is a potential function, right? If you change from C to D and go back, it's the same thing.
If I change from C to D?
Yeah, if you change the strategies, you're not summing like a memory to it, right?
There is some sort of memory that I will show later. I'm not sure. This is just a standard prisoner dilemma game. So I'm not sure if it's a potential function. That I don't remember. I don't remember if it's a potential function. But it's a standard. I mean, this equation, if you neglect this term, this is exactly the same equation that Luca discussed in the first lecture for two populations. So let me just, because this is a conference in a school in evolution, so let me say, so a framework that is not my framework, but what we did can fit in this framework. And the idea is that now you have these populations or histograms or probability distributions, or you can also represent it with neural networks, okay, interacting among them. And the idea is that these individuals need to learn about the environment, they need to learn about the others. And they do so then by a quantity that is very, you have already heard of this here, and it's very common in machine learning, the Kullbaum-Leibler divergence between the two probability distributions. The probability distributions are parameterized, say, if these are Gaussians, for instance, parameterized by the mean and the variance. And so individuals can tune the mean and the variance, trying to fit the model to the environment they see, to the other agents. And this is interpreted by the authors like the fitness of the agent I with respect to agent J is the distance or the Kullbaum-Leibler divergence between the probability of individual I and individual J. Okay? Now, what happened here is that there's a distance between probabilities, and that is very interesting is that even though the minimum, the optimum of this, actually it should be like minus, I think, minus, because the optimal behavior will be if this if these two parameters are equal. That's the minimum of the curval level divergence. That's where the two probabilities are equal, and so I'm representing, the agent is representing very well the system, the environment. Yes.
Comparing from one player to the other,
Absolutely.
not necessarily is going to be the same.
Absolutely.
So you're breaking the symmetry of the game.
Abs-
So both players should be the same, have the same outcome.
Not necessarily, not necessarily.
Not the same outcome, but they respect the same rules.
Yeah.
So when you're dealing with divergence, I don't see how you can compare the two populations.
Yeah.
For example, player J is going to be different. The divergence from J to I is going to be different from I
Yes,
to J.
absolutely. That's why. Yeah, this is not my framework. This is Hidalgo's framework. But the idea is precisely that different individuals have different fitness. Now, they use the standard parameterization in machine learning. When we are learning from the environment, we use this kind of, this direction of the, now, let me say, precisely what you mentioned, the asymmetry between in the KL divergence, that's key. That's the key point here.
Because if you're selecting one player, that player will be better than the others because there's no symmetry there.
Yes?
And that's, you're changing the rules that you established first.
No. No, because, no, this is not the game as before. But you just have, this is like a machine learning algorithm can be built up to here, and you can define, actually the symmetry is here, because look at this. Fitness of I with respect to J is I and J. Now, if you want the fitness of J with respect to I, it's exactly the same function, only that the parameters are reversed, because you have switched the players, okay? And they use this metric because it's the standard metric in machine learning. So they imagine you are, these are agents that are learning about the environment, and so they use this is a standard metric in machine learning. Now, the fact that, of course, when you flip players, they have different payoffs, and the question is, who will win? That's the idea. But this metric is the standard metric to train neural networks, okay? So now, precisely what you point out, the asymmetry is what is key here. Because what happened is that the difference between these two guys, if you think that this is player B, and this is player A, and player B is just a little bit different, the parameters are a little bit different from player A, okay? So you can expand and tailor and everything. And what happened is, because the curval level divergence is 0, when the two parameters are the same, so the expansion in Taylor, the first term is 0, okay? Also, that's a minimum. The curval level divergence is convex, that's the global minimum, and so the first derivative is also 0. What remains then is the second derivative. And the second derivative is the Fisher information. It's called the Fisher information that measures somehow the responsivity of the system, okay? And what happened, and if you expand this, I will get the second order derivative will be evaluating beta E, and this will give me the Fisher metric at beta E. And on this guy, it will give me the Fisher metric at this parameter here, beta E plus delta beta, okay? So what happened then is that when the Fisher information, if this Fisher information for beta E, for A, is larger than this, sorry, if this is a smaller, or let me say larger than this will be positive, and then this guy will be fitter, in the sense that the KL divergence is smaller. The KL divergence is smaller. Then the message of this paper is that due to this asymmetry precisely, and this fact, agents, the situation, although the optimal situation will be all parameters equal, that situation is unstable, and the instability will move towards larger and larger values of the Fisher information. Now, the Fisher information is closely related to the responsiveness of the system. In physics, it's very closely related to the susceptibility of the system. So it will diverge, and they show with simulations how all the populations go and diverge. All the population converge to a point where the feature information diverges. So, okay, this is just one slide, experiments. This is a paper, this is work but by different people. Oops, this guy fall. This is a work by different groups, but we have been following mostly one of the leading researchers in this area is Ángel Sanchez in Madrid, Carlos Tres de Madrid. So he has done several experiments with humans, and he has summarized recently here in a perspective article what he considered the main experimental results. I'm non-experimentalist, so I cannot judge the experimental results myself. But let me just go back here a little bit. And the question is this, because of this analogy with evolution and learning, because of this analogy, and because of this result that obtained here, Nowak, that a structure or network is called network reciprocity. Sorry. It's called network reciprocity, that the network can help cooperation, okay? So because of this, and because of this similarity with evolution, so people have been trying to model human cooperation. It could be different from animals, bacteria, everything else, but human cooperation has been modeled in a very similar way as in biological systems, as in evolution, where some individuals, essentially when the fittest reproduces faster, essentially that means, essentially you are comparing the fitness of the guys. For instance, let me give you an example that I have here. This algorithm here is precisely players imitate the best. So that means that the player has to look at the payoff of the neighbors, okay, and compare the payoffs and imitate the best, okay? Now, Ángel Sanchez and collaborator, they have found, and they mentioned.
What's the intuition for one type of networks not leading to cooperation and others leading to cooperation?
That's challenged precisely here in these experiments. But the intuition is that, for instance, in the two extreme cases, in these two extreme cases that I show here, okay, the intuition is that in this case, agents, because there is a dimensionality, because there is a dimension, they can form clusters that isolate these guys that are inside the cluster. They are isolated from outside the vectors. It's similar like in the Ising model when you have a cluster of spins pointing in one direction, and those spins out the boundary are paying an energy price for that. But the energy term of the cluster is much better. I mean, the energy is minimum inside the cluster than what they lose because of the boundary, if you are familiar with that kind of argument. More or less,
I'm familiar with that, but my confusion was that when you were doing microscopics with just a few agents, you were showing that cooperation was bad, right? Then I'm lost, because if you would tell me that cooperation is good for short neighbors, I understand that they could form clusters where cooperation is good. But I'm a bit confused, because before you showed that with two or a few agents, they will not cooperate, right? And now you are saying that here,
oh no, yeah, okay, I understand.
The agents are not connected to the ones far away, so
yes.
like there are only a few. So why do they start cooperating?
Okay, yes, I understand your question there, absolutely. No, because this thing here that I mentioned, yeah, it's just two players, and there is no learning here. There is no repeat. This is not a repeated game. This is played once, okay? And when it's played once, and you think that an agent just took the rational decision, they are rational enough to compute the optimum, then they will end up with no cooperation. Now, but what happened here is that you have repetition, okay? And then, for instance, in repetition, you can imagine you get reputation or things like that, okay? So you are repeating the game, repeating the game, repeating the game. Now,
how do you know so fast that in this one on the left that you will not have cooperation? Because when you explained that on the left have no cooperation, you stated that it was obvious, but based on all this learning, why don't I get that some of these guys start cooperating?
Based on this algorithm here, there are many algorithms. So based on this algorithm that was introduced by Nowak, okay, it's simple. This guy here is defecting and is interacting with all the neighbors, okay? and all the other neighbors are interacting with him, okay? Because this guy is defecting, his payoff is larger because all others are cooperators. So he is a defector interacting with defectors. Sorry, a defector interacting with cooperators. Because of that, his payoff is larger. The payoff of this guy is larger than the payoff of all of these guys. Now, the second step of the algorithm is that now you will compare. Every agent will compare with all the neighbors. Now, every agent that is a cooperator will have a defector, will have this defector as a neighbor. And so when they see the payoff of that guy, that payoff is larger, so they will imitate it. And then you have, in one step, essentially you have cooperation collapses. If we do updates, parallel updates.
But if I take a blue guy, you will see order n square interactions that worked well, right? Where they both cooperate. Because there are n square interactions there, and n square of them were good, both cooperated, right?
Who?
Blue with blue.
Blue with blue.
Blue with blue, they cooperate, right? So that's good. And there are order n square of those.
Yeah, but it's much better when you defect and the other cooperate.
But there are only n of those, right? Because the res one is only one that has to connect with n of the other one. So there are n bad events compared to n squared.
No, but the algorithm, no, but this is the difference because game theory is a little bit different from physics. So is because we are in a, we are not optimizing one function. This is if you think of optimizing, when you are trying to optimize, the function changes. This is the landscape changes. When you try to optimize, the landscape moves. So this is not an optimization problem. So in that respect, it's different from physics. But there is no n square order here as in an Ising model. There is no n square because what the algorithm says is that each agent will compare only with n neighbors and will take a decision individually of what the others are doing. So every agent will only look at n neighbors. No agent will look at n squared.
No, I don't think that's what I said. I did not say that. I said that he looks at n neighbors, and each neighbor has n interactions, right? And so he looks at the neighbor and says that n minus 1 times the neighbor cooperated and it was good, and once it was bad. So I don't know. I mean, I could imagine one algorithm which says the maximum or the minimum of the outcomes. That's what I take. But one where I average, it looks like it will be very different.
I guess if I can rephrase it also from my understanding, he's looking at n neighbors and it sees n square interactions which are positive, okay? And then it says one interaction which is defective. Is there any weight factor that weights in the fact that it's much more beneficial than much more detrimental? If you have a weighting factor somewhere, this can be cured, although it must be like that.
No, it's like this. This guy also interacts with n cooperators. And he wins because he defects. Look at this payoff matrix here. Okay? Look, when both cooperate is 1 year. When both cooperate is 1 year, the payoff. But when one cooperates and the other defects, is 20 years of jail.
Yeah,
so it's much, much worse. It's much, much worse.
It's a weighting factor because if there
Yes.
was 0.5 and 0.7, it would be worse. So
Yeah.
it's a weighting factor.
Yes, of course. Yeah. Oops, sorry. And indeed, that's why the dilemma appears. Okay. If this is not this large, okay. Yeah. So these experiments that were carried out by, as I say, Angel Sanchez, Anso Sanchez in Madrid, Zaragoza. I will summarize the result. I cannot say all what they do, but the main result he summarized here in a perspective article in 2018, where he criticizes the idea, the fact that theoretical physicists started building a lot of models of human cooperation, building it as biological models, okay? But in one particular aspect that he mentions is that there is no evidence out of his experiments, there is no evidence that indeed individuals compare payoffs when they learn or when they play a repeated prisoner dilemma game. So this essentially seems to I don't think it really contradicts, but according to Sanchez, this contradicts the evolutionary models that compare payoffs as the replicator equation and all these things. So he calls for other type of models. However, I will show later why I disagree with this. Now, there is not just what he finds here, for instance, is that this is the probability of an agent to cooperate. This green light is the probability of a random agent, a generic agent, to cooperate if he has cooperated in the previous round, and this is the number of neighbors that have cooperated in the previous round. So it says, okay, if I cooperated the previous round, and in the previous round, this is the fraction of cooperators that cooperated, the more cooperators cooperated, the more I will cooperate in the next round. So it's sort of a prosocial behavior. So I'm taking into account what's going on, what the others are doing around me. But what happened if I had played defection in the previous round, it will have the opposite trend. So he called this mood, the mood. So depending on the mood, or what I did in the previous round is my mood, and what others did is like the paying attention what others did, the social component, and also they call this moody conditional cooperation, okay? And he observed it in lattices, he observed in heterogeneous networks, and he doesn't see differences. Also another metric that he tried to see is this mean cooperation. This is an experiment with about 600 humans, and again, lattice and heterogeneous networks, and he tried to see at how the global cooperation, the total cooperation in the system evolves out to 52 rounds. And he said, well, there is no significant difference in behavior in the statistics that we find. So there is no really clear evidence that there is network reciprocity. So there is no network reciprocity. So lattice means that these are about 600 individuals or human beings that are put to play a game on a computer, a prisoner dilemma game. So in the computer, they can just click cooperate, defect, as they like, and then they are showing the screen how much they receive, the payoff. So now lattice or heterogeneous is how the experimentalists, how they connected the computers. So if the computers are connected in a topology of a lattice, then agents are interacting on a lattice. It's like if we organize all here in a lattice and we start playing with our neighbors. It's precisely that, but using computers.
The computer only knows what the neighboring computer is.
Yes, they connect it in such a way that only.
Heterogeneous one?
And the heterogeneous one is just they try to emulate. It's a small network. It's 600, about 600 individuals, but they try to emulate the statistics of a complex network. So they try to emulate a power law in the distribution of the degree of the nodes. But it's a very small network, so compared to the kind of network we study in physics. Does that answer the question? Or?
Not precisely, but maybe you can go on.
Okay. So now let me introduce the model. It's based on a model called, introduced initially by Kammerer, which was a more complex model. It has been also studied recently by Tobias Gala in Manchester. So the idea of the model is, okay, this is the payoff that I will receive in a game that he plays with J if he cooperates. And J plays this strategy, which could be cooperation or defection. And this is the payoff I will receive playing with J if he defects, and the other player plays the same strategy that could be C or D. Now, the difference is like the incentive to cooperate. Okay? If this difference is positive, it means that it's better to cooperate. So I have an incentive to cooperate. If the difference is negative, then I prefer not to cooperate. Now there is something that includes the drive to cooperate that takes into account memory effects.
It behaves just like the risk factor in potential games, right? Because I'm seeing there that you're going to incorporate rationality. It's somehow related to noise.
Yes, but I'm not familiar with the potential theory that you are mentioning. So there. It's just, I'm here, no? So this is just a standard game theory. I'm just taking the subtraction of 2 payoff, okay? Because this is the incentive to cooperate. Now, the drive to cooperate is, okay, it depends not only on what happened in the round right before, but it happened what happened in all the past history of my game, okay? So this is a way to emulate memory. So for instance, if this is the parameter of memory decay. If this parameter is 1, so you see that this is a recursive equation here. So this D, this is the drive, is updating recursively. And so when alpha is 1, this guy disappears. And so the drive is just what happened in the previous round. There is not memory. If alpha is 0, this thing is essentially this is equal to this plus is a linear cumulative of incentives. A linear cumulative of incentives, something like this, but grows cumulative with time, assuming that this remains constant, just to give you some intuition. This is very complex stuff because this change in time and is also changing in different positions of the network. But just to give you some intuition. So if this is constant, then and alpha is 0, this will grow like a line. And if the opposite, alpha is 1, this is 0, so this remains constant on time. And in between, you have some kind of exponential tendency towards this value here. So there is some memory loss. There is some memory loss. This will be full memory, full cumulative memory, and this will be some memory loss. Now, with that, now the probability to cooperate, I can write it like this: the probability to cooperate given this drive and given this parameter beta, I can write it like this also, just a strategy, the probabilistic strategy that I can play is written just like a kind of Fermi rule, where I have, it's kind of a Fermi rule. So you have the drive here, okay? And so you will get, remember, you have this probability and you have this drive. So if you want to have the full thing, you can just put this equation here, you can put it here. This is what you see here. Okay, but before I do that, now this is usually in all these games, this is called experience-weighted attraction learning algorithm. In this, people usually study just the payoffs. Which are the payoffs that I gain, and all the learning is based on that. But I also have, now what we did is we added, I was working with Julian Drighetto from Institute of Cognitive Science and Technology, so she knows more about cognitive science, social sciences. They do experiments with humans, so they have more experience with that. So they have been developing some works where they suggest that there is also a normative drive, okay? And so this normative drive, according to research done by them and this kind of behavioral experiments and things like that, I really don't know much about, there is, we build this kind of function out of that, which is, first of all, self-consistency. Well, this is a variable, this S variable here, is a variable that could be 1, is 1 if I cooperates, and is 0 if I defects, okay? So this thing here is plus if I cooperates, and is minus if I defects, okay? So this could be plus, this is a positive parameter, so it could be plus or minus. So this could help the drive or could diminish the drive to cooperate. And this has to do only with what I does. And this they call this self-consistency, that according to some theories of psychology or cognitive science, I really don't know much about that, we try to be consistent with ourselves. So what we did before, we want to do again, in order to build a story of ourselves and feel relief. So there is this part here then is taking into account what others do. It's essentially the norms that I perceive. So this N here is the number of cooperating neighbors at round T. And there is an interaction here. The idea that self-consistency enhances social influence. If I'm being self-consistent with myself, I am more receptive to what others do. That's the idea. But essentially, this comes from the experimental results by Sanchez that I showed, that the moody conditional cooperation. And depending on my mood, so my mood is here, depending on my mood, I cooperate more or not. If this is 0, I defect. This is 0, there is no term. helping. All this is positive. If this is 0, there is no term helping to increase the drive to cooperate. So that's the model, and this is based also on, this is a recent book, like 2015 or something, where neuroscientists are also realizing that humans are not just as economics has assumed in the beginning of the maybe 20th century, that humans are just selfish. Actually, they are very prosocial in many situations, and they have studied also the neuroscience of that. They have realized that there are regions in the brain, I don't know which region it is, but there is a region in the brain that process individual payoffs, so what I care about, and the very same region in the brain also process information about others. So essentially, that region is coding these two things, the same region. So now, what I was saying before, now I plug, remember now this utility function now contains a normative drive. A normative drive, this is delta U. So now I plug this thing here, I obtain this equation that's doing the math, and now this is an iterative equation that gives me the probability at t plus 1, the probability to cooperate at t plus 1 given the probability to cooperate at t, and the utility at time t. So this is just, all the memory essentially disappears, is now here in this iterative equation is the memory, but now we don't have this individual drive that was kind of complex. Now, because now we are analyzing games on networks, and games on networks, what they do in the experiments is an agent played in pairwise games with the neighbors independently. But I chose one strategy, and that strategy I play with all my neighbors. And then I collect linearly, I just sum all the payoffs with my neighbors. Because of that, I will have a term linear in the number of people who cooperate, because it's just a sum, okay? This is just, this will be effective parameters. I mean, the calculation will give me this, but it's kind of long stuff. But, and this thing here comes from the self-consistency thing, or the normative drive that I was saying, okay? This thing here, that is the interaction between self-consistency and what others do, this comes from the third term that I was showing before, from this term. And now there is also a term here. So this guy here contains the payoffs, individual payoffs, and also it contains information about what others do. And this is collected in these effective parameters. Now, you have heard about this here already, this kind of thing. Now, I have this equation, okay? I see this is the probability to cooperate at t plus 1, given this probability to cooperate, and given this delta U. And this delta U depends on n. So essentially it's given S and n, the number of cooperators. So this is similar, but it's not the same, but it's similar to this kind of graph. This equation is similar to this kind of graph. And we see that this graph is kind of linear in the experiments. And this graph can be linearized with a small beta by expanding on a small beta. By the way, I forgot to mention, beta is like a rationality parameter, as you were mentioning. Because if beta is 0, I essentially play randomly. I don't care about the payoffs. And if beta goes to infinity, I want to optimize the last drop of the payoff, okay? And so, because these experiments suggest we could essentially kind of expand, but this is not the same like this, it's just similar. I will come back to this later. But I could expand on beta, a small beta, so this, later on we will see that this is self-consistent. Not here, but this suggests that beta could be small. And let's assume alpha is also small, which is, well, kind of consistent with some experimental result, but just let me take it as an assumption, and we check self-consistency at the end, okay? So we know that suppose these are the individual actions, for instance, they move very fast. This is the fast variables that some lecturers have been mentioning here. So if they are very fast, then I can essentially make what is called the adiabatic approximation, which is like, and in this case, for instance, I take batches of the relevant changes happen in certain batches of actions of t. And I expect t alpha in this approximation, t alpha to be much less than 1. And then this will allow me, because now I have all these very fast actions moving, this will allow me to average out, to take the average in this interval. So I have my delta U is this, that depends on these variables that are discrete and stochastic, right? But because of this average that I can do here, I can replace this guy by just the average value, which is the probability to cooperate, and this guy here, which is the number of the number of neighboring cooperators, so cooperating neighbors. So this n is essentially the sum over the neighbors of I of the probabilities of j. This is essentially the Adiabatic approximation here. And so I have delta U becomes a function only of probabilities. No stochasticity anymore. There is no stochasticity anymore. I just have, if I plug this thing here, I change this stuff by this, what I get is a nonlinear equation, iterative equation. So we have this guy here. Now, we say that according to the experiments Anso has been doing, and also some theoretical work he has been doing, there is then not much evidence that networks affect cooperation in the case of humans, as they seem to do in the case of bacteria and other life systems, living systems. So in the case of humans, it doesn't seem to be much impact of topology, okay? So I can essentially do a mean field approximation if there is no much influence of the structure, and then I can take this, essentially drop the index of the agent everywhere. And this will be just, for agent I will be just one single x, and the sum over all the individual will be just the number of neighbors times the same x, okay? And this is essentially the mean field approximation. Mean field approximation. And then this is a second change, right? We change first from here to here, from stochasticity to deterministic, and then now we shift from networks to just one single agent. Now we have just one single agent, okay? Notice that we have a quadratic term here. This quadratic term here comes from the self-consistency interacting with what others do, which is kind of the Moody conditional cooperation stuff, kind of, okay? And then I have the linear term here because the sum of the payoffs and because I pay attention also to what others are doing. And this is the self-consistency condition. They come from the self-consistency condition, okay? So now, let me then show you now the analysis to obtain the phase diagram of the model. We assume, okay, these are the experiments, and we assume, the assumption doesn't seem to be very good, okay, but otherwise we didn't know how to proceed. I think this is our first work, so really this is the first exploratory work we did in this. So the idea is, do you see the cooperation here? It seems to kind of reach a stationary state. Not exactly, but it seems like. So let us assume that the experiment indeed reached a stationary state, okay? And also, let us assume that this transient here doesn't seem to be very relevant. So let us also assume that we can neglect the transient, such that only the stationary state contributes. So, and the stationary state of the dynamics would be, remember that this equation became now an equation on a single variable. It's an iterative equation of one single variable. So, when we compute the fixed points of those equations, okay, we get the typical equation of a fixed point, and this fx is exactly this function here, which is very similar to the people who are familiar with. This is very, very, very similar to what you obtain for the Ising model, okay? The only difference is this quadratic term that comes again from the interaction of the self-consistency, my mood, with what others do, okay? That quadratic term comes from that. So if that term, the self-consistency interacting with what the others do, is neglected, is taken to zero, we recover exactly the mean field equations of the Ising model. If we replace magnetization, will be given by this, okay? Because we are working here with 0, 1 variables, and this is usually plus or minus 1. So this function here, you can see that this is here in the argument of the hyperbolic tangent, there is a parabola. So this is essentially a parabola here, okay? And this will be the minimum of the parabola. The parabola takes the minimum at this point, and this will be the minimum value of the parabola. But then it's stretched by this hyperbolic tangent. So a parabola goes to infinity, but the hyperbolic tangent doesn't allow to go to infinity because the maximum of the hyperbolic tangent is 1. So this saturates here, and we get this kind of shape. And depending of the values of A and Y0, this curvature will move, okay? If this is very flat, I will only have one fixed point in all parameter regimes. Now, this is the minimum. The minimum of the parabola here coincides with the minimum of this function. The position of the minimum. So the minimizer here. Now, if I move the minimizer, I can move this rigidly. This whole curve, I move it rigidly. And so I can find different regimes. If the curvature is large enough, I can have regimes where I have one fixed point, where I have two fixed points, and where I have no fixed points, and again I have one fixed point. So this is, according to doing the analysis of that more carefully.
Can you go back? What's the y? It's just a parameter.
Yes, it's because, you know, I have been simplifying and simplifying, so I have to pack more and more parameters into effective parameters. Otherwise, this will be a mess. These are effective parameters that depend on the original parameters of the model. Okay?
How would I get x squared in the Ising model?
How do you get that, sorry?
If I wanted to get really an analogy with the Ising model, how would I generate the x squared in the Ising model language?
In the Ising model language, to generate the square, well, if you like, you can define an energy function. I don't know what that will mean at this point, but you will just define an energy function, I think, that contains three-body interactions, maybe.
Three-body interaction? Well, could you write it down? How would it look like?
But I don't know exactly. I'm just saying because the standard Ising model only has pairwise interactions. And pairwise interactions, due to the pairwise interactions, I will obtain this kind of equation, right? This is because of the pairwise interaction. Because it's like one single spin is interacting with all the others, right? So this is like the effective field. Yeah? And then if you take also the mean field here, you have to sum over this, you get the tangent, right? So this gives you linear term in M. You see that there is just, so I will expect, but I'm not sure, I will have to work it out, but I will expect that if I have three-bar interactions, then a mean field model in three-bar interaction, I will expect maybe, you see, now I have one mean field here. If you allow me, as I say, I have to, okay, so just one spin here, and then if you allow me just to do something that is not correct, but just some intuition, this is K, you get two mean fields, yeah? And so you get an M squared. That's what I would expect, but I mean, I will have to study carefully. But that's the intuition I have, yeah?
But remind me, why is that natural from the game theory point of view, this cubic interaction?
No, there are no cubic interactions.
Yeah, so that's what I'm...
Okay, no, I understand what you mean. No, because this is the... let me go back. I think it's here. This is a pairwise interaction, yeah? But... yeah, but this thing here, this is a pairwise interaction, yeah? The pairwise interaction is here. And this Fermi function comes from the other spin that we are not seeing, which is which action I take. Let me draw it for you maybe it's more clear if I do it, because I wanted to write it like this because it's simpler, but I can write that function it's a Fermi function, so let me that's why I'm working with deltas. You see that I'm working with deltas everywhere? If instead of working with a delta, I work with U in this case, instead of the dry, because the dry is more complex, but let me do this one here, the delta. So instead of the delta, I work with U. Like a U of cooperation, for instance, or defection, I think cooperation. And then I have U.
Well, let me ask, maybe it helps. So the final equation for the Ising model, you could start there and explain the meaning of that equation, right?
Mm-hmm.
You could say this is the interaction. Could you do the same with your final equation? Because the algebra is hard to follow, but at the end you got a very simple equation. Can you explain that equation?
Yes, I'm trying to do it here. When you have an Ising model, for instance, you have an Ising model, you can think of the probability of one single variable of spin up, for instance. Then you get a plus here, and you have to normalize that. And then you get a plus, and a minus here. Yeah? The probability of the marginal of a single spin. But now you can divide by this, so you can just obtain like something just like this. But I want to emphasize, here is already the spin, you see? Here is a spin up. This is the other spin we are not seeing. There is a spin here, a spin up, here is a spin up, and here is a spin down. This is why we get plus and minus in the Ising model. Plus and minus. Plus because I calculated the marginal of spin up, okay? The probability of spin up. So, but now if I put this down, then I get essentially minus UD minus UC. There is something. Let me just, I'm trying to do just something very simple. Like when you have this S over H, and then you have here SH plus E minus SH. Now you divide by this, so you just get 1 over 1 plus E, and this gets here, SH, okay, twice, SH. Okay.
What you're, if you're explaining where the tangent comes from, I know where the tangent comes from, and I understand that equation. M equals tangent.
What I want.
Sinh over cosh
Yes.
is probability, and sinh are the two possibilities.
Yeah.
It's plus minus sign.
But
I would like the analog of that explanation of that equation for your final equation.
Yeah, that's what I want to emphasize. When you get the tangent here, okay, you have a spin here, a spin up, a spin down, okay, and that thing is in this shape, in this Fermi rule. Is because there is already that spin hidden, okay? And that spin sort of interact with all these things. They interact with all these things because this is like the energy function. This looks like the energy function. This is here. And this is like the external field, okay? And there is another spin. And this is the three-bar interaction. But game theory is not the same like physics. I'm just trying to provide intuition. You get an energy term. This energy term has up to 2 bar interactions. Here, 2 bar interaction. But the Fermi rule, this stuff contains already a spin, another spin. The one that we are, in this case, is the agent. The agent that I'm looking at. I'm fixing only one single agent. That single agent, the strategy of that single agent is reflected in this Fermi rule. So that's another variable that is already in this form, okay? Maybe,
yeah. See, my point is that those equations are very hard for me. I need too many letters, and I don't remember where they came from. So those equations are hard, but I had some hope that I could understand the final one because it was much simpler.
I understand, because that's why I try to put also draws, because it depending where I present, people understand differently, right? So when I present at NASA, for instance, I was presenting draws, and they say, oh, I'm not understanding anything. Show me the equations, and the equations were very ugly because we spin class theory. So I understand. So we can try to discuss this further, and I try to make it clear for you. So, but I think that the math speaks more clearly and more precisely. So, but yeah, this is the idea. Is you have a two-bar return, but this stuff here. This stuff is like either the effective field, okay. And this is the effective field that the agent I feels. And this is where you have the three-bar interaction. But this is not the same. It's not the same. Game theory is not the same like physics, because in physics we optimize, we minimize energy. In game theory we don't minimize. Okay, in game theory we look for Nash equilibrium, which is different from optimization. So.
Where did the cubic interaction? Okay.
You can see here quadratic term, and this is the agent I that I'm not is not presented there, but I can show you later at the end. I can get back to a slide I have upwards that the equation is different, and I'm sure maybe it's more easy there to see. So once you have this equation, yeah, you get this stuff, then you calculate analyzing these fixed points, okay, doing the math, we can get this. Remember that there are now 3 effective parameters, A, X, Y. So I have A is the 3rd dimension, X0 and Y0, okay? And we have this kind of surface, 3-dimensional surface, okay? It's a little bit complex here, but let me just show an example here, okay? Fix A. I fix A to a given value, and here A is equal to 5. And then I can see a surface of this 3-dimensional plot. And this guy here produced this triangle, and this guy here, kind of triangle, and this guy here produced this kind of parabola. Okay? Inside this parabola, there are no fixed points. And inside this triangle, there are 2 fixed points. And outside, there is only 1 fixed point. Okay? And these points here is where these regions finish. When these regions finish, I got critical points. So I got a line of second-order phase transitions here, line of second-order critical points. So I have, these are the guys at criticality. We can compute here, for instance, the susceptibility and see that it diverges and so on and so forth. We want to get more intuition. Then I fix here, for instance, Y0 to this value. And I see that I'm traversing the different regions. But now let me fix Y0 and A, and let me just look what is the cooperation X as a function of the parameter X0, just to have a look at this. Then you see first you have a lot of cooperation, high cooperation, and then there is a region of biostability. It looks very small, but there is a region of biostability. Then it jumps here, and then there is another single equilibrium here, and here there is non-equilibrium, and then again back to equilibrium. This is this part. Okay, and well, now we can see these are the critical lines, and we do the inference. I will show, if you would like to see the math. I don't think it's very relevant, but we have to face some technical difficulties to do the inference, but we do the inference of the experiment, for instance, in the lattice, and it's here, and the closest point, because this is a whole line of critical points, the closest point is about 11% distance. And the experiment in the heterogeneous network is about 3% of the closest critical point in the line. Okay, so this is, now all this stuff, all this model, of course, is kind of mean field. So we have only 600 humans, so really we have to look at the finite size effects and all this stuff. But this is just, as I say, the first work on this thing. Now, well, this is how we do the inference. We have to face some technical difficulties, but I don't think, unless you want to look at that, I don't think it's relevant. Moody conditional cooperation is obtained now. If I get back to the original equation, when I have this delta U, I have not yet done all this Adiabatic approximation, okay? But I have done the mean field approximation. I neglect the I's, all the indexes. You can forget about the indexes here. And now I can plug again back the stochastic equation here. So this can be interpreted, this equation can be interpreted exactly like the probability to cooperate at the round t+1, given that I cooperated and n of my neighbors cooperated, and the probability for me to cooperate all at time t, given this. Now, this curve here is without this x. I have to get rid of this x, because this curve here only has, after c, after d, is this variable. What I did in the previous round, c or d. And this axis here is this variable, okay? So this variable should not be there. And so in the article, I did a little bit of math probability theory to just get rid of this probability. But in the case of having just one single stationary state, when we have monostability, then this is just a fixed point. And if we are in the stationary state, all history is lost. And then this is exactly this, but evaluated at the fixed point. And this is where I said that at the fixed point, now I can expand on beta, if I like, can expand on beta. Actually, this is what I did. To estimate the parameters, I expanded on beta, okay, to linear order, because delta U contains these values here. And then from this plot, I take the parameters of these lines, and then I find a map between the parameters of the model and the experimental data. Okay, and this is what we do inference. This is a key point here because that's a constraint we have to impose, and that allows us to define the prior because we did some Bayesian inference. So that's a way I define a prior. So these are the results. As I say, this is preliminary. I'm not plotting, this is just analytical calculations. I'm not plotting like the standard error bars, or the confidence intervals or things like that. Just, I have the matrix, the covariance matrix if you want to see, but I don't think that's relevant now. But I have here the experiment, and this is the line we obtained for the heterogeneous network. Okay, so it's a fit that doesn't look too bad. And this is the other kind of curve. These are the experimental data. This is the line that feeds experimental data, the dashed line. And these are our theories here without linearization. There is no linearization. Here I use this full kind of Fermi function. So it's consistent. So it's self-consistent with the linear approximation that we did at some point. It's self-consistent in order to have the adiabatic approximation. So, and the same happened with the lattice. Here we have a better agreement, even though we haven't quantified, apart from the covariance matrix that I have. But I think it's just a theoretical study. I think it's kind of good for such a simple model, simple tractable model. Okay. So, what is the effect of the parameters? These two parameters are key, but I don't think this is relevant now. Let me better go ahead. This is also simulations we did. This is more complex elaborations that we can obtain, more complex equations we can obtain when we do full probability theory instead of just assuming a single fixed point. It's a complex equation, but what I want to highlight is that I have now a distribution of agents here that I didn't have before. I only have one single individual. Now I have a distribution of agents, and this is also experimental results. Also, they have measured the distribution of cooperators. So we simulate now this is full stochastic agent-based model on nets. There is no analytical stuff here. All is the full agent-based model on networks. And we simulated, and now here we have experiments and simulations on different networks. We have a random network, a static network, a dynamic network. And all of them are very close. This is a very exploratory work. We just published in GAME, so we really didn't spend much time on this. It was to look at. But now you see, with this equation, this is the probability. This stuff here comes from, this stuff here are these lines. So it comes from this equation. Taking into account this histogram by trying to do some ansatz here. And ansatz is a beta distribution. Here we obtain this kind of equation. Okay, but I think this is not relevant. I think what is relevant are the perspectives, and I want to go a little bit quick on this. So it's strange that these experiments are not showing network reciprocity. It's that simple. I don't think human cooperation should be that simple. There should be something. So I think we have to do some theoretical work to understand what happened with networks and also what happened with stochasticity. And this is just to show you an example of a different thing. This is a work that I did in Manchester with Alan McCain, Tobias Gala, and Max Friedkirch. This figure was presented by Ricardo. These are the semi-arid ecosystems. And this is just to show you an example of what happened when we have demographic stochasticity. When we take into account not the mean field theory that I did, but when we take full. These are the equations, these two guys here are the equations that Ricardo presented. These are the two equations. This is the water. The idea of this thing is that you have a rain, and then if you don't have plants, then the land is very arid, and the water cannot infiltrate into the land, and so it just run away very fast. Instead, if there are vegetation close by, then the land is not that arid, and the water can infiltrate more easily. But it's much faster the diffusion of the surface water, and this is what we have here. This is the equation for the soil water that infiltrates. This is the surface water, the water run away. And well, these are the parameters. This was shown by Ricardo. But the difference is that the plants we assume here are individuals. This is a theoretical model. We assume individuals equal. So, it's just a theoretical model we wanted to study because it was very curious that the people at the region where Ricardo is, where there is Pacala and Princeton around that region, there is a lot of humidity, there is a lot of rain, and so the trees there are very, very packed. A lot, vegetation is very dense. And they were doing individual simulations, so a very dense vegetation, but they were doing individual-based simulation, taking into account the sun that are here, all the nutrients that come from here, the size of this, the form of this, are very, very complex high-performance computing they were doing to try to simulate this very dense vegetation stuff. And then Pacala found out at some point that they can do just a mean field, and it works extremely well. But this stuff is very far away from that range. We expect here individuality, because it's very scarce, the plants, should play a relevant role. So we define a stochastic model. This is piecewise deterministic stochastic model, and that mentioned Paul in one of his lectures. He mentioned this kind of technique. And we see here that some of them, this is the deterministic model. The deterministic model is the equations, we replace this by the equation that Ricardo showed. And the deterministic equation predicts extinction, while the stochastic model predicts that it's going to extinction, but at some point, it recovers. It was work. So I think stochasticity plays a relevant role, and the question is how to do that in humans. Second slide, second perspective that I see, well, we need new experiments in order to really test criticality more carefully, more theoretical work, okay. But we can also start thinking what happened when we have global interactions or global influence, because up to now, we have seen only what the norm are, okay, should I finish? Okay, now? Okay. Oh, well, just to mention then, this work we did with Ricardo Sequina. You can use spin glass theory techniques to compute this stuff. You can have a norm that is global norm, rather than just also local. You can have a combination of the local norm that I perceive from my neighbors and also globally, say, for instance, from TV, and we can do some math about that. And if you give me some time, I can tell you what I think is the most relevant thing out of this, okay? And we was having a discussion at lunch, and I think one of the task of science is to turn taboos, what we call taboos, into science, into real science, right? So I think I presented this work on cooperation. The real goal of the work I have presented up to now, the real goal, was to see that nobody reacted negatively against it. So it's normal that I study human behavior using physics tools. And nobody is complaining here about that. We have biologists and we have physicists here. I'm happy that it's the first time that I have them together. So 60 or 70 years ago, I don't know, this stuff will have been considered crazy. If I say I will model human behavior with physical tools, people will tell that I am crazy, that I am total nonsense. Well, that changed. Let me tell you another taboo that is very, very exciting today. That was a taboo that destroyed careers. Just an inoffensive word. One inoffensive word that destroyed careers, according to leading neuroscientists, they say that it used to destroy careers. So they avoid to mention that word. Now you have papers in Science, Nature, Physics Review Letters, Physical Reviewing, about that, using that single word, inoffensive word, in the title. And that word is just consciousness. There are experiments now doing, and this is a lot of stuff going on. I don't know if everybody's aware of that, but there are a lot of interesting things going on. If you want to speak about that, I will be happy to speak later, but there is no time. So let me tell you now a different kind of taboo. No consciousness, a different kind of thing. Now let me show you this kind of stuff. This is done by one of the leading teams in quantum physics in the University of Vienna, Anton Zeilinger, 2018. PINAS. An agent, simply an agent, a robot that is learning how to do experiments. This is a very complicated algorithm that they use, really. I don't follow all the details that they use. I think it's very complex. But it's just an artificial agent performing quantum experiments. There is no issue with that. You have an agent, this is artificial intelligence. Okay? Now, let me do this. Let me do this. Einstein had this advice that we should try to describe the real factual situation. Okay? Curtis Callan, 2 days ago, I think, put this advice in a very nice statement. So I copied what Curtis Callan said on Wednesday, and he said essentially what I would say is the real factual situation. He said, we do not directly measure the hidden variables. We use statistical inference, to see through the noise into the underlying physical parameters. This is a nearly universal method in modern physical science. I would say this is the closest I have seen to the real factual situation. What we do when we do science. So this is more or less the situation. What we do when we do science, this is a robot that is performing science in some way. So all this week, we have seen physics tools to help biology. But can biology help physics? Usually we physicists tend to believe that it's the most fundamental physics, and then others need our help. But can biology help physics? So, this plot, I just changed one thing, and physicists that have shown this in the last year, they react very negatively against this, very angrily. I just changed one robot for another physical system, a neural system. We have biologists here. One moment, okay. So, if you like, if you prefer, you can put a robot. Now, if you analyze what does it mean to do an experiment, you have some circular interaction, kind of circular causality, which is very common in cognitive science. And I will finish with this. The DNA. Have you ever wondered why the DNA is made of 2 strands and the brain is made of 2 hemispheres? This is a self-referential task. I need to replicate, the DNA needs to replicate itself. The brain this is a way to refer to itself. The recursion theorem of computer science says so. I have some work on this. And now I'm finishing. But before I say my last statement, I want to thank you and say goodbye, because I think after this statement, I will be thrown away from Brazil. The statement that I will do is the following. These 2 things, this and this together, give me, when I analyze the dynamics of this stuff as a probabilistic model, give me equations that look like the equations of quantum dynamics. Thank you.
Okay, so we are running really late, but I think we have time for a few questions.
Well, there is one thing that I didn't get in your equation. So when you write this interaction term, the sum over J should exclude I.
Yeah.
essentially. So, which means that that term is not exactly the magnetization.
Absolutely. Yeah, and the spin glass is very important. When it's a spin glass, it's very important.
Yes.
Yeah, I know.
In the spin glass, it is very important, and also in these games, it plays quite a role.
I agree. I agree.
And so, are you taking this into account?
No.
You don't not?
I was just to give some intuition to him that I moved to physics, but I understand. That's what I have been emphasizing. Game theory is different from physics.
So this is why you get this quadratic term in M, or
the quadratic term comes from here. Because in the definition of normative drive that we say, we have an interaction between the decision of the player. Is it the decision of the player? Yeah.
Can you just say a few words about how these experiments with humans are done? I mean, how do you set up the network?
Oh, that's a tough question because I'm not an experimentalist. I know that what they do is, I mean, I imagine they have some room, right? And they have some tables in the room. For instance,
600 players, right?
Yes. Okay. Well, no, you can have them far away via internet, but you can connect topology that you want. You design the topology, but of course the network is virtual.
Thank you for a nice lecture. I have two questions. The first one is more related to technical stuff, and the second one is more related to ethics. The first thing is, do you think that this model can reproduce, actually it's just one question, do you think this model can reproduce kinds of games that were historically played in unethical experiments? For instance, the experiment of the classical psychological experiment of the prison. And do you think that this model incorporates the importance of status and kind of roles in human communities?
I don't think it. No, I don't think it includes status. I think it's a very simple. I think it's one of the minimal models we can think of that include the main ingredients that we need. So I don't think that it has all the complexity that you will need to go there. Does that answer the question?
How can you tell that every player is rational?
I'm not saying that. What
No, because you assume that beta is smaller than 1, right?
Because, yeah.
And beta is rationality.
Yeah. It's actually irrationality when beta goes to 0. Yeah.
So you're assuming that players are extremely rational.
Yeah.
That's in the experiment.
I don't have an explanation why they behave like that, but it comes from this. The intuition comes from this plot. You see, this plot is linear.
Yeah.
And this plot is very similar, as I say. It's not the same because first I have to compute the fixed point and evaluating the fixed point and so on. But it's similar to this expression. You can span in beta, and when you span in beta, you get equations for a straight line, okay? When beta is small.
Yeah,
and so it's consistent.
Yeah,
but,
I understand that. But the experiment that I'm thinking, for example, if one guy that is playing the game is maybe drunk, he's not going to behave like this, right? He's not going to be rational. It's going to be more like random.
Yes, I don't know how they chose the people to do that. Yeah, I don't know. That's important, yeah. I think maybe they, okay.
Okay, so let's thank John again.
Thank you very much. Can I press here?
Yeah, just turn it on.
You're spending all this time to explain the experiment. You don't know what the experiment is.
No,
You can't tell me details about the experiment. Why do I want you to details about the model? The whole point of the model is to explain the experiment.
No, but display the results. Right? The results.
The model is experiment. With
Yes.
experiment. How can you possibly make a model?
But I thought it was clear. I mean, there's a lot of details in this kind of experiments, of
No,
course.
the experiment must be trivial.
No. With humans, they have to take ethical concerns. They have to take into account how the screen appears to the human being. So they have to be, even in the paper,
It's live or not. You can't even tell me. They could be 100 miles away.
they can be 100 miles
10
away.
years difference.
No, they can.
If it's all by computer, who cares?
They can. I have introduced first a figure of that, but I realized you like it to see equation, so I changed it.
No,
but,
I don't like to
but
say
yes.
it. I want to understand the
Yeah, no, the point is that so this whole work is you've done everything because you saw this experiment. You were trying to explain it, but if you don't know the details of how it was done, how can you build a model that explains?
Because I have collaborators. So I was working with people from cognitive science that they do experiments with humans. So I collaborate with them.
Well, then you should have asked them what the experiment was.
And I also.
I mean, I think that's your fault, not their fault.
Well, you also have to take into account that this work, honestly, was done in my free time. So I really didn't have time to dive into this game.
Well, that's
So,
like that.
Let me ask the question, these systems of yours,
is what?
this kind of things, models you showed, I mean, do they show extreme events which in nature happen? I mean, one extreme event would be, for instance, let us say what happened 2 days ago in Venezuela. That would be an extreme event of human cooperation, human behavior.
Yeah, that's
I
something.
mean, will they appear in your model, this kind
That's
of
something
thing?
I'm very interested in. In this model, I think I will have to introduce something, for instance, immigration. So whether for instance, immigration, for instance, immigration of
immigration?
defectors, for instance.
Ah.
So there are defectors coming into the system, for
coming
instance,
into the system.
and suppose they are defectors. So how much they can sustain before they collapse? That's a question I'm interested. That is related to resilience, but it's like work I'm doing.
Anyway, I have to assimilate. But where are you from? Colombia?
I'm from Colombia.
Ah, okay. Yo soy argentina.
What? Okay. What is your name?
Eh?
What is your name?
Hilda Cervera.
Ah, you're Hilda. Okay.
Yeah.
You work here.
Yes, yes.
Ah, very nice.
Okay. Okay. I wonder, I mean, I work in not exactly in this entrance that I work in, but I work in chaos, long big systems. I also work with epilepsy, but that's not the same thing. Epilepsy is large data, not even big data. It's not the same thing. But I wonder